Imagine a time long before time as we know it, before Earth, before the sun. Picture a vast, cold and dark cloud floating in the endless ocean of space. This cloud, a stellar nursery, was immense, stretching for light years across the cosmos. It was made of the simplest stuff in the universe, hydrogen and helium gas sprinkled with tiny grains of dust. These were the leftovers from older, long-dead stars. For millions of years, this cloud just drifted, a quiet and patient reservoir of cosmic potential. It was a place of serene darkness, waiting for a spark to ignite the grand performance that was to come. Everything we are, everything we know, was once part of this unassuming cloud. Then, something disturbed the peace. Maybe a shockwave from a nearby exploding star, a supernova, rippled through the cloud. Or perhaps the gentle gravitational pull of a passing star was enough to stir things up. Whatever the cause, this cosmic nudge was the trigger. The cloud began to collapse. Gravity, the quiet and relentless architect of the universe, started pulling the gas and dust inward. Little pockets of matter grew denser and denser. Slowly, almost imperceptibly at first, the cloud began to spin like a figure skater pulling in their arms. The more it collapsed, the faster it spun, a celestial dance beginning in the void of space. As the cloud spun faster and faster, it flattened out into a huge rotating disk. We call this a protoplanetary disk. Think of it like a cosmic pizza dough being tossed in the air, spreading out from a dense center. At the very heart of this spinning disk, the material became incredibly crowded. The pressure and temperature started to climb to unimaginable levels. The atoms of hydrogen gas, once floating freely, were now squeezed together so tightly that they began to fuse. This process, nuclear fusion, unleashed a tremendous burst of energy. In that brilliant moment, a star was born. Our sun flickered into existence, lighting up the spinning disk of gas and dust that surrounded it. The young sun was a beacon in the darkness, a powerhouse of light and heat. Its birth marked the dawn of our solar system. The vast majority of the original cloud's material, over 99.8% of it, had been consumed to create this new star. The remaining sliver of matter, less than 1%, continued to orbit the newborn sun in that flattened disk. This leftover material, this cosmic debris, might seem insignificant, but it was everything. It was the raw material from which entire worlds would be built. The stage was set, the central star was shining, and the next act of creation was about to begin. The story of the planets was just getting started. With our sun blazing at the center, the rest of the protoplanetary disk was a chaotic and dynamic place. It was a cosmic construction site, filled with dust and gas swirling around the young star. Not all parts of the disk were the same. Close to the sun, it was incredibly hot. The intense solar wind, a stream of charged particles blowing from the sun, pushed away the lighter gases like hydrogen and helium. Only heavier, rockier materials could withstand the heat. Tiny grains of dust, made of iron, silicon, and other metals, started sticking together. Think of them as cosmic dust bunnies, slowly growing larger and larger through a process called accretion. This was the beginning of the rocky inner planets. These dust bunnies grew into pebbles, the pebbles clumped into rocks, and the rocks smashed together to form boulders. Over millions of years, these boulders collided and merged, their mutual gravity pulling them into larger and larger bodies. These planetesimals, or infant planets, were the building blocks of worlds. Some were only a few miles across, while others grew to the size of small moons. The inner solar system was a demolition derby of these rocky bodies, each one on a collision course with its neighbors. It was a violent but creative process. Through countless collisions and mergers, the largest of these planetesimals swept up most of the debris in their paths, carving out their own orbits and growing into the worlds we know today. Further out in the disk, beyond a boundary we call the frost line, it was much, much colder. Here, it was cold enough for not just rock and metal to exist, but also for volatile compounds like water, methane, and ammonia to freeze into solid ice. This meant there was a lot more solid material available to build planets. So the planetesimals that formed in this outer region grew much, much larger. They started as rocky cores, just like the inner planets, but they quickly became massive enough for their powerful gravity to pull in the vast amounts of hydrogen and helium gas that filled the outer disk. They ballooned into the colossal gas giants. This is how the two distinct families of planets in our solar system came to be. Close to the Sun, where it was hot, we got the small, dense, rocky worlds: Mercury, Venus, Earth, and Mars. They are made of the heavy stuff that could survive the Sun's heat. Farther out, beyond the frost line, we got the enormous low-density gas giants, Jupiter and Saturn, and the more distant ice giants, Uranus and Neptune. They had a head start with their icy cores and became gravitational titans, gobbling up the primordial gas that the inner planets could not hold on to. Our solar system was taking shape, a place of fire and a place of ice, all orbiting the same star. The first 100 million years of our solar system's life were anything but peaceful. This was an era of cosmic violence, a time we call the Late Heavy Bombardment. The newly formed planets were not alone in their orbits. The space between them was still cluttered with leftover planetesimals, asteroids, and comets of all sizes. These cosmic leftovers were like billiard balls on a table with no pockets, constantly crashing into the young planets and moons. The surfaces of the inner planets were relentlessly pummeled, creating scars that are still visible today. Just look at the Moon or Mercury. Their cratered faces are a testament to this violent and chaotic youth. During this tumultuous period, our own planet, the young Earth, experienced a cataclysmic event that would change its destiny forever. A rogue protoplanet about the size of Mars slammed into the molten, still-forming Earth. We call this impactor Theia. The collision was unimaginably violent, an explosion of rock and fire on a planetary scale. A colossal amount of molten debris from both Earth's mantle and Theia was blasted into orbit around our planet. This ring of superheated rock and vapor didn't just dissipate into space. Instead, gravity worked its magic once again, pulling the debris together. Over thousands of years, this material coalesced into a single large spherical body. This new celestial body was our Moon. This giant impact hypothesis explains so many things about the Moon. It explains why the Moon is so large compared to its parent planet, why it's made of rock that is chemically similar to Earth's mantle, and why it has such a small iron core. The Moon began to orbit the Earth, and its gravitational pull had profound effects. It stabilized Earth's wobble, preventing wild swings in our climate that would have made it difficult for life to evolve. The Moon's gravity also created tides in our oceans, a rhythmic sloshing that may have been crucial for stirring the primordial soup where life first emerged. That ancient, violent collision gave us our constant companion in the night sky. This era of giant impacts wasn't unique to Earth. Every planet and moon in the solar system was a target. A massive impact might be responsible for Venus's strange backward rotation. Another could have knocked Uranus onto its side so that it spins with its poles pointing toward the Sun. Mercury's large iron core and thin mantle might be the result of a hit-and-run collision that stripped away most of its outer layers. These early chaotic collisions were not just destructive, they were formative. They shaped the planets, set their rotations, and gave them their moons. The solar system we see today is a direct result of this brutal and creative beginning. For a long time, we thought the planets formed in their current orbits and stayed there, like perfect clockwork. But, the more we study our solar system and others, the more we realize that the early days were much more dynamic. The giant planets, in particular, were not stationary. They migrated, moving inward and outward in a gravitational dance that reshaped the entire solar system. Jupiter, the colossal king of the planets, likely formed closer to the Sun than it is today. Its immense gravity began to pull it inward, scattering smaller planetesimals and clearing a path through the disk. This journey had dramatic consequences for the inner solar system. As Jupiter moved inward, its gravity would have been a wrecking ball. It may have disrupted the formation of a full-sized planet in the region between it and Mars, leaving behind the jumble of rocks we now call the asteroid belt. Some models even suggest that Jupiter's migration was responsible for delivering water-rich asteroids from the outer solar system to the inner planets, including Earth. This Grand TAC model proposes that after migrating inward, Jupiter was pulled back out by the gravity of the newly forming Saturn. The two giants fell into a gravitational lockstep, a resonance, and together they migrated outward to their current positions, their dance profoundly altering the architecture of the entire system. This planetary shuffling didn't end there. Another major event, known as the NICE model, proposes a later period of instability among the four giant planets. Jupiter, Saturn, Uranus, and Neptune. Initially, they were in a much more compact configuration, but their gravitational interactions eventually became unstable. This instability sent Uranus and Neptune spiraling outward into the icy outer reaches of the solar system. As they moved, their immense gravity flung trillions of icy planetesimals, the leftovers from the planet formation era, in all directions. Some were thrown out of the solar system entirely, while others were sent hurtling toward the inner planets. This gravitational upheaval likely triggered the late heavy bombardment, that intense period of asteroid and comet impacts we talked about earlier. The outward migration of Neptune and Uranus sculpted the outer solar system, creating the Kuiper Belt, a vast donut-shaped ring of icy bodies beyond Neptune, where Pluto resides. It also created the Oort cloud, a theoretical spherical shell of trillions of comets at the most distant edge of the Sun's gravitational influence. The solar system we see today is not a static museum piece. It is the result of a dynamic and sometimes chaotic history of planetary migration, a grand dance of giants that set the final layout of our cosmic neighborhood. After the chaos of the early solar system subsided, Earth began a long, slow journey of transformation. Initially, it was a molten ball of rock, with a surface temperature hot enough to melt lead. Volcanoes spewed gases into the sky, creating a thick, toxic early atmosphere. As the planet gradually cooled over hundreds of millions of years, water vapor that had been trapped in the atmosphere began to condense. It started to rain. It rained for centuries, maybe even millennia, filling the vast basins and craters on the planet's surface. These were the first oceans, the cradle of life. From a distance in space, our world began to take on a distinct bluish hue. Sometime in these warm, shallow, nutrient-rich waters, something extraordinary happened. About 4 billion years ago, simple organic molecules, perhaps delivered by comets or forged in deep-sea volcanic vents, began to link together in complex ways. They formed self-replicating structures. This was the dawn of life. The first living things were simple single-celled microbes, but they were a profound turning point in our planet's history. For billions of years, these tiny organisms were the only inhabitants of Earth. They slowly changed the planet, with some evolving the ability to perform photosynthesis, a process that uses sunlight to create energy and, as a byproduct, releases oxygen. The release of oxygen by these early cyanobacteria was a revolution. It was also a catastrophe for much of the life that existed at the time, as oxygen was toxic to many early microbes. This great oxidation event fundamentally changed our atmosphere, paving the way for more complex, oxygen-breathing life to evolve. The sky turned from a hazy orange to the familiar blue we see today. An ozone layer formed, shielding the surface from the sun's harmful ultraviolet radiation. Life was no longer confined to the oceans. It could now venture onto the land. The stage was set for the explosion of biodiversity that would eventually lead to plants, dinosaurs, mammals, and, very recently, us. Our planet is a testament to the intricate interplay of geology, chemistry, and biology. Its history is written in its rocks, its oceans, and the very air we breathe. Earth is not just a passive stage on which the drama of life unfolds. Life has actively shaped and transformed the planet, just as the planet has shaped life. The existence of liquid water, a stable climate moderated by the moon and a magnetic field, and a rich geological history all came together to make our world a habitable oasis in the vastness of space. This pale blue dot, as the astronomer Carl Sagan called it, is a precious and perhaps unique outcome of the solar system's long story. For most of human history, the solar system was a realm of myth and mystery. The sun was a god, the moon a goddess, and the planets were wandering stars that foretold the future. We were the center of everything, and the heavens revolved around us. This Earth-centered or geocentric view of the cosmos held for millennia. It was a natural conclusion, born from our everyday experience. The sun does appear to rise and set, and the stars do seem to wheel across the night sky. It took a revolution in thinking, a courageous leap of imagination and intellect to see our true place in the universe. That revolution began in the 16th and 17th centuries, with thinkers like Nicholas Copernicus, who proposed that Earth was not the center, but instead orbited the sun. This was a radical, even dangerous idea. Galileo Galilei then turned a new invention, the telescope, to the heavens and brought back the evidence. He saw moons orbiting Jupiter, proving that not everything revolved around the Earth. He observed the phases of Venus, which only made sense if Venus orbited the Sun. He saw the mountains and craters on the Moon, showing it was a world, not a perfect celestial orb. The old model crumbled, and our modern understanding of the solar system, our true cosmic address, began to take shape. The 20th century propelled us from observation to exploration. We developed the technology to break free from Earth's gravity. We sent humans to the Moon, letting them walk on another world and bring back pieces of it for us to study. We launched robotic ambassadors, tireless explorers that have visited every planet in our solar system. The Voyager probes flew past the gas giants and are now journeying through interstellar space, carrying a golden record with the sounds and images of Earth. Probes like Cassini orbited Saturn for over a decade, revealing the secrets of its rings and moons. Rovers have crawled across the surface of Mars, searching for signs of past life in its ancient riverbeds. These missions have transformed our understanding from abstract knowledge into a vivid, tangible reality. We have seen the towering volcanoes and deep canyons of Mars, the sulfuric acid clouds of Venus, and the swirling Great Red Spot of Jupiter. We have sampled the solar wind, landed on asteroids, and peered into the icy plumes erupting from Saturn's moon Enceladus. Each new mission, each new image, adds another piece to the grand puzzle. We have learned that our solar system is a place of incredible diversity and wonder, far more complex and beautiful than our ancestors could have ever dreamed. Our curiosity has carried us across billions of miles, turning points of light into worlds we can explore. Today, in the year 2025, we live in a golden age of solar system exploration. Our Sun is a stable, middle-aged star, about halfway through its 10 billion-year lifespan. The planets orbit in a state of relative calm, their chaotic youth long behind them. We have detailed maps of Mercury and Mars, we've listened to the winds of the red planet, and we've peered through the methane haze of Saturn's largest moon, Titan. We understand the basic story of our solar system's formation and evolution. Yet, for all we have learned, the solar system remains a place of profound mystery. The more we discover, the more questions we find ourselves asking. Some of the biggest questions are about life itself. We know life thrives here on Earth, but are we alone? Mars once had liquid water on its surface. Could microbial life have started there, and could it still exist deep underground, hidden from the harsh surface? The moons of Jupiter and Saturn, like Europa and Enceladus, hide vast liquid water oceans beneath their icy shells. These oceans are dark and cold, but they may contain hydrothermal vents, just like those on Earth's ocean floor where life flourishes without sunlight. The search for life, or even just the chemical precursors to life, is one of the greatest drivers of our exploration today. Finding it elsewhere would change everything. Other mysteries lie in the very structure and history of our cosmic home. Is there a ninth major planet, a so-called Planet 9, lurking in the darkness far beyond Neptune? The strange, clustered orbits of some distant Kuiper Belt objects suggest the gravitational influence of a large, unseen world. What is the true nature of the Oort cloud, that immense, ghostly sphere of comets surrounding us? And can we piece together the story of planetary migration with more certainty? Understanding our own history is key to understanding how planetary systems form throughout the galaxy, and whether Earth-like planets are common or incredibly rare. The story of our solar system is not over. It is still being written, both by the slow, grinding processes of cosmic evolution and by our own relentless curiosity. Future missions will drill into the ice of Europa, fly drones through the atmosphere of Titan, and return samples from Mars. New telescopes, both on the ground and in space, will peer at the outer reaches with ever greater clarity. The journey that began with a collapsing cloud of gas and dust 4.6 billion years ago has led to this moment. We're a part of the solar system, humanity, can look back and try to understand the whole. The greatest discoveries, perhaps, are still ahead of us, waiting in the darkness between the worlds.